If you're working on a game and your objects are simply passing through each other, then this video is for you. What you need is a component in your physics engine that handles the collision of rigid bodies. In this series, we've already seen how to handle the collision of simple particles, as well as the rotation of rigid bodies. This video will be a natural extension of those topics, guiding you step by step on how to implement rigid body collision in your projects. Before we get started, I'd like to say a big thank you to Jorge, who recently joined the 3D Underground. If you too would like to support this channel, you can do that at patreon.com/ogldev or by joining the YouTube channel as a member. Okay, same as with simple particles, we have collision detection and collision response. As I've mentioned in the video on particle collision, the topic of collision detection is huge and very complex, so we will use the simplest algorithm, which is a bounding sphere. It's good enough for many cases, and I hope to cover more advanced algorithms in the future. So let's focus on the collision response of rigid bodies. Let's start with the basic concepts. When two objects collide, they exert a massive force over a tiny fraction of time. We call this an impulse. Our entire mathematical goal is to find this vector, which in physics is commonly represented by the letter J, so that's what we will use here. The impulse is the change of momentum of an object when the object is acted upon by a force for an interval of time. As you probably remember from a previous tutorial, the momentum represents the quantity of motion that an object possesses and basically tells us how hard it is to stop or change the course of a moving object. To calculate the impulse, we will need a few geometrical elements. First, the normal vector between the center of mass of the two rigid bodies. Next, we have the contact point. This can be quite complex to calculate precisely, so we will simplify, not surprising, using the bounding sphere. Multiply the normal vector by the radius of the bounding sphere of one of the objects, and subtract the result from its position in world space. We can now calculate the vectors from the center of mass to the contact point for both objects. These are crucial because they determine how much the force causes the object to rotate versus translate. Next, we calculate the velocities at the contact point. Why is this important? Imagine a ball hitting a spinning fan. If it hits the fan at the center, and assuming that the center doesn't spin because it's covered in some way, then we have a simple bounce. But if it hits one of the blades, which is spinning very fast, it is sent off across the room. So we have to account for how fast that specific area at the contact point is moving due to the spin. The velocities at the contact point are calculated using a cross product between the angular velocity vector and the vector from the center of mass to the contact point. Remember that the angular velocity is a vector which is perpendicular to the surface of rotation. Incidentally, this is also the tangent vector to the bounding sphere. We saw this in the video on rigid body rotation, so make sure to watch it. We can add this tangent vector to the linear velocity vector and get the overall velocity vector of the body. Think about how the Earth rotates as it travels through space. At this point, we have an opportunity for an early exit from the algorithm. While this calculation should only take place for objects that are touching, they may actually be already separating from one another. This can happen when the collision was already processed in the previous frame, but the objects didn't move enough, so the collision might still be detected by the implementation. You know, epsilons and numerical stability. We can calculate the relative velocity by subtracting the two velocities at the contact point and projecting the result on the normal vector using a dot product. If the result is positive, it means the objects are already moving apart. We are now ready to dive into the core of the impulse calculation. We will start with Newton's second law and write the acceleration explicitly as the change in velocity divided by the change in time. Let's multiply both sides by the delta time and define the impulse to be the force times the delta time. This makes sense intuitively because the impulse is active for a very short period of time. We can now calculate the change in velocity. Next, we have the impulse direction. We know that the impulse always pushes directly along the collision normal. Why the normal, you ask? Well, it's a bit of a simplification, but it is well grounded in actual physics. For example, Newton's third law says that for every action, there is an equal and opposite reaction. In the real world, you will also need to handle friction and the fact that actual collisions include some measure of compression and decompression of the materials, so the actual calculation is very complex. We should definitely make our lives easier. So we can say that the impulse, or capital J, is equal to the normal times a lower j, where j is the magnitude of the impulse vector. So we get this for the first object, and the opposite for the second object. Well, different masses of course, but you get the idea. Now let's consider the angular change. Hitting an object off-center causes a change in its rotation. This is Newton's second law of rotation. The angular acceleration is the change in angular velocity over the change in time. We do a series of substitutions to get the following. Since torque is the radius cross the force vector, and the impulse is the force times the delta time, we can write the following. We now need to consider the relative velocity. This is the velocity that the two objects are closing in on one another. For example, if a car that is going at 60 miles per hour hits a car that is going at 40 miles per hour exactly from behind, the collision speed is not 60, it is actually 20 miles per hour. Subtracting the velocity of one object from the other tells us how fast the gap between them is shrinking before the collision or growing after the collision. We usually use a subscript of minus or plus to distinguish between before and after, respectively. Newton observed that for a given pair of materials, the ratio of the speed after a collision to a speed before a collision is a constant. He called this constant E. This is the coefficient of restitution. This is also a term that you should be familiar with from a previous video, so in a nutshell, this coefficient tells us how elastic the collision is. It goes between 1 for a fully elastic collision, where no energy is lost, and 0 for a fully inelastic collision, where all the energy is lost, so the objects stick together. Since the objects change direction due to the collision, we have to add a negative sign to flip the velocity. We actually care only about the velocity along the normal, because the bounciness rule only applies to the head-on part of the collision. So we need something to filter in just this part, which is the dot product, of course. Remember that the dot product projects one vector on another. So we get the following. In the actual code, you will see that we use the average between the coefficients of the two objects. I think this is only fair to do that. So we know that the velocity after the collision equals to the velocity before the collision, plus any change to the linear as well as the angular velocities. Now the problem is that we can't really add a linear change, which is measured in meters per second, to a rotational change in radians per second. We already saw that the change in rotation is given by the following formula. So we do another cross product with the vector from the center to the contact point to get a vector that represents the linear velocity at the contact point, which is induced only by the rotation. With everything that we have developed so far, we can do a series of substitutions and extract the impulse. This is pretty much mathematical grudge work, which is easy to get wrong, so I'll just put the steps here and let you review it offline. Now that the impulse has been calculated, we can turn it back into a physical force and use the following steps to update the linear and angular velocities of our objects. So that was quite a lot of math, but we can actually implement all of it in about 50 lines of C++. This is done in a new function of the rigid body class called calc collision reactions. The function follows exactly the steps that we saw and is annotated with comments, so I'll let you go over it offline. It takes a reference to the rigid body that this object is colliding with as a parameter, and at the end we can see that the linear and angular velocities of both objects are updated. But where does it fit into the entire system? Let's go back to the main update function of the system class. We can see that we start by applying the global forces to all objects. This is a new feature that I've recently added. When initializing the system, you can provide a global force, which is always active. Gravity, most likely. At the end of the function, we reset all forces, so if you have a constant force in the application, you have to set it on every frame. But you don't need to worry about gravity. The system can take care of it for you. Just provide it as a global force. Next, we handle the collisions between point masses, and finally, we have a new function that handles the collisions between rigid bodies. We use a similar logic to what we did with point masses, going over all the objects and checking for collisions between each pair of objects. Notice that for each element in the outer loop, we traverse from the next element until the end in the inner loop. We get the collision status between the pair of rigid bodies, and if they are touching, we call calc collision reactions. You may remember that checking for collision between point masses used to be a Boolean operation. They could either be colliding or not. But there is also the possibility that they are overlapping when we didn't handle the collision in time. So the function getCollisionStatus was expanded to detect such cases where the distance between the objects is less than the sum of their radiuses. Also notice that we no longer check that these two distances are equal to consider this to be a collision. Due to numerical instability, it's always better to calculate the absolute delta between the distances and declare a collision when the delta is less than some epsilon value. Back to the function that handles collision between rigid bodies, we have a new function to handle the case when they are overlapping. This is actually very simple. Remember that at this point the current frame hasn't been rendered yet. We still have a chance to save the world. All we have to do is back up the objects a bit and fix the overlap. We just need to calculate the vector between the center of mass of the two objects and its length. To move the objects from an overlapping status to touching, we need to increase the distance between them by the delta between the minimum distance, which is the sum of their radiuses, and the actual distance, which is lower. So we normalize the vector between them and scale it by the amount by which we need to increase their distance. Then we cut this vector in half because each object will move by half of the required distance. Some people divide the distance based on the mass, so a bigger object moves less. Something you may want to consider. In this case, I'm going with the simplest solution. We can now add half of the distance vector to the position of one object and subtract it from the position of the second object. Overlapping solved. Notice that we actually calculate the impulse first and only then take care of the overlap, which might seem counterintuitive. The reason is that if we resolve the overlap first, It's kind of like hiding the full scale of the collision from the physics solver. Going back to the main update function, after handling the collisions, we do the usual sweep over all objects, particles and rigid bodies, and update their positions. Finally, all the forces are reset. So I was just about ready to wrap up this tutorial when I suddenly realized there was a major problem with the implementation. The normal vector is calculated between the centers of the bounding spheres, and the radius vectors are calculated from the same locations to the contact point, which is somewhere along that normal vector. This means that whenever we do a cross product between the radius and the normal vector, we get 0, so there is no angular effect. I had a feeling that the behavior of the demo was not good enough, but I guess I needed to be more suspicious. Anyway, the problem is that the radius vector needs to be calculated from the center of mass to the contact point, and not from the center of the bounding sphere, unless you want them to be the same, of course. So the contact point is still along the normal vector, which goes between the positions of the objects. This implicitly means that the position is also the geometrical center of the object, which makes sense, you know. We already maintain a center of mass vector in the point mass class, which is specified in local space. We are just not using it here. So the solution is to transform the center of mass to world space, and we have the function to do that from the tutorial on angular rotation. This function creates a rotation matrix from the orientation quaternion of the rigid body. It transforms the local space coordinate using this quaternion and adds the result to the position of the point mass, which is already in world space. We can now calculate the two radius vectors by subtracting the world space position of the center of masses from the contact point and continue as usual. Also make sure to initialize the center of mass to something other than the origin. We can see that the results are much better now. And that's it for rigid body collisions. Now this is a simplified model. We've intentionally ignored things like friction, air resistance, and etc. to keep the math approachable. This is just the foundation, and we will improve it in the future. So thank you for watching, and I will see you next time.